Hello Geometry, Mr. Fugay. Welcome to our video. This is the second part of our angle applications. Part one was talking about how we can use mirrors to generate similar triangles to find heights. This is going to be a second application. It's also going to help us find the heights of things we otherwise wouldn't be able to find. But this time, rather than using a mirror, we are going to use the sun, the power of the sun and the power of shadows. So as you can see here below, I have a picture of a tree and then I have a picture of a wall. And if you look at them, and I'll highlight here in red, the wall has some height and it has some type of shadow that's from it. If we connect the ends of those together, you will create a right triangle. And I'll highlight that here by sliding it up so you can see it. Okay. Well, we can do the same thing with a tree. So I can draw my tree top to bottom, find its height, which is ultimately what we want to do. We can measure the shadow of that tree, and then we can once again connect those together. Now, these two triangles that I've just created are actually going to be similar to each other, just as we discussed with the mirrors. Now, why is this? Well, we need two angles in order for this to work. The first angle is going to be the same that we had with the mirrors, and I'll use, let's see if I can use a bright blue for this. So we have these right angles here that are created by the tree and the ground and the wall and the ground. But the second shadow, the shadow is generated by the sun. And so we have the sun somewhere up here. It's my great drawing of my sun right there. And the sun's rays are going to reflect the same angle among the tree and the wall. Of course, they need to be in semi-close proximity to each other, but the angle of the sun is hitting both of these objects at the same exact angle. And so ultimately, the angle down here at the bottom that's made with the shadow and that diagonal are made by the sun, and since the sun is hitting at the same angle, this is angle again. So in summary, the wall and the tree are perpendicular to the ground. That's our first set of angles, and then the shadow is created from the angle of the sun. And so when we take these two things together, this is our angle similarity, which means we can use proportions to help us find these missing heights. So let's look at a couple examples of how this works. So in this first example, I have a fire hydrant that is 2.5 feet high, and it's going to cast a 5-foot shadow. Then we have a street light, which I want to know what the height is, and it casts a 26-foot shadow at the same time. We want to figure out what the height is. So we'll start with the fire hydrant here, and let's use black for this. So the height of the fire hydrant is 2.5 feet. The shadow length of the fire hydrant is 5. The shadow length of the light post is 26 feet, and ultimately what we're trying to figure out is how tall this is going to be. So even though you may not see it, I can connect the diagonals there of the top of the shadow and the top of the actual object, and we can see that we have two similar triangles created. So my proportion is, and there's different variations of this, is I'm going to take the height of my light post X and write it as a ratio over the height of the fire hydrant. So I'm comparing the two heights and saying that they're in the same ratio as the shadow lengths, 26 and 5. And so from this information now, once a proportion is set up, we can use cross multiplication to help us solve. So this is going to be 5x, and 2.5 times 26 is 65. Divide both sides by 5, and then we're going to get our missing height of the light post, which is going to be 13 feet. So 13 feet is what we're looking for in this first problem. Let's look at one more where we have to actually create the picture ourselves. So it says a tree casts a shadow that is 31.38 meters long, and there is a man who is 1.72 meters tall. They cast their shadow at 3.4 meters long. So let's draw a really quick picture of this. So I have my tree, okay? And then I have my person. So we'll draw them somewhere else off in the distance, okay? The tree's shadow that we are now being told here is 31.38 meters long. So that's going to be the bottom side of the triangle that's going to be created here. So that dotted line is just the imaginary third side that makes our triangle. Our person, who has a height of 1.72 meters, okay, there they are listed there. We have their shadow as well, and their shadow is 3.4 meters long. Once again, we'll connect that imaginary dot there to make our triangle. We want to find the height of the tree. So from here now, we're going to set up our proportion. I typically like to do like the height of the tree as x, and then write that as a ratio over the height of the person, 1.72. We set that equal to, now we come back to the tree and pick 31.38 as the shadow of the tree over the shadow of the person. So we're matching corresponding sides to each other. We'll go ahead and do that cross multiplication. So we get 3.4x for my first cross product. 1.72 times 31.38 is going to give me 53.9736. We could probably round that up to 54 if we want here. So because 97 would just round up to 54. Divide both sides by 3.4. 54 divided by 3.4. And once again, rounding here is okay. We'll round to the nearest tenth. So I get 15.88 or 15.9 meters since we're talking about meters. So the height of our tree will end up being 15.9 meters long. So just imagine what a meter stick is. Imagine 16 of them stacked on each other. That's essentially what the height of the tree is. So there's one problem for you to try, example number 6. And this is a similar question about finding the height of a stop sign and the shadow. We want to then compare that with a tree casting a shadow. So I'll leave that for you to do after the video. We have one last example that we're going to take a look at on the next page. And this one is a little bit trickier. So I want to read the question first, and then I want to visualize it for you. So it says, the sun is shining down in Philly today. The Philly fanatic wants to find the height of the bell at Citizens Bank Park. The fanatic is 6 feet tall, and they cast a shadow that is 2.5 feet long. The fanatic shadow, and our key word for this problem is coincides with the end of the shadow cast by the bell, which is 21 feet from the fanatic. What is the height of the bell? Of course, we got to throw a Phillies reference in here. At the time of the recording of this video, the Phillies just lost the NLCS, so there we have it. Okay. What are we going to look at here? Well, let me try to visualize this for you. So forget the fanatic that's in your picture here. I drew a much boring looking fanatic as a green blob here that has its shadow, okay? And what I'm going to show you here as well is that the bell, the Liberty Bell that's at the ballpark, has its own shadow. So let me just go ahead and shade in what that would look like, okay? So that scribble that I just put in here, that is the shadow of the bell, all right? So what's happening here is my fanatic is walking along. They're walking along, and notice that they have a shadow too, and they're going to walk into the shadow of the bell. So as they keep walking, they keep walking, they keep walking to get to the spot that they're at, you'll notice that the end of the shadow right there, so the end of the shadow that we have right here is lining up to the end of the shadow of the bell. This is what I mean by coincide. So when I use the word coincide, it means that essentially it's overlapping. But more specifically, it is overlapping so that the ends of those shadows, all right, are going to be touching each other. So overlapping or meeting, whatever you want to use as an alternate synonym for the word coincide, okay? So let's try to analyze what's going on in this situation, okay? So what we have here is I'll use the light blue to represent the bell. So the bell has a height, and then the bell has a shadow, and I'll bring that shadow to about here, okay? And I'll do my best to draw a line to connect those. So that blue triangle is the bell at Citizens Bank Park. We also then have the Philly fanatic. So I'll use bright green to denote the fanatic. So they have their height right here. And notice that the triangle that's created by the Philly fanatic is within or inside of that triangle, okay? Well, let's label the information we have, and then we can separate these triangles into our separate drawings. So we have, let's see, first thing, the fanatic is 6 feet tall. So the height of the Philly fanatic will be 6. And they cast a shadow that is 2.5 feet long. So we'll go ahead and make this distance right here 2.5. The shadow coincides with the end of the shadow. We've already established that. The bell is 21 feet away from the fanatic. So the fanatic, looking at where they're at, is exactly 21 feet from the bottom of the bell at Citizens Bank Park. Okay, and I'll extend that to go to the center of the bell. So what we have there is that information, and we're trying to find the height of the bell here. Okay, so if I draw these triangles out separately, as I've talked about with overlapping triangles, it's really helpful to sometimes draw them separate from one another. So for the fanatic triangle, we have a bottom side of 2.5 and a height of 6. Now for the light blue, the height of the bell is x. That's what we're trying to find. Now, the length of the shadow of the bell is not going to be 21, and that's what's really, really important to capture in this lesson, is that the 21 is only going to get me from the center of the bell to where the fanatic is. And so that additional 2.5 feet is also going to be part of the shadow. So the bottom length of this is actually going to be 21 plus 2.5, and that's going to be our biggest difference here. That's going to be 23.5 as the shadow of the bell. Once you get through that challenge, the setup now for our proportions should be much easier. The height of the bell is X, the height of the fanatic is 6. The shadow of the bell is 23.5, the shadow of the fanatic is 2.5. We now are just going to cross multiply and do the math to get our final answer. So that's going to be 141 divided by 2.5. And so the bell at Citizens Bank Park is approximately 56.4 feet. So the height of the bell, let's write that over here in our final answer. The height of the bell is equal to 56.4 feet. So it's really important in problems that use the word coincide to make sure that you realize that the one shadow is fully within the other triangle, a triangle within a triangle. And like the other examples we've done, I do have one for you to try here, number 8. So we have, once again, a person that is inside of a shadow of a building. So very similar to how the fanatic was in the shadow of the Liberty Bell. So example 8 is for you to try as well. So that'll conclude our shadow application problems. Of course, the first thing I would recommend to try to do are the 2 examples we didn't do, which is example 6 and example 8. Start there first, and then I'll have some additional practices to help you refine your skills and get a little bit stronger with this topic. Hope this video was helpful, and I hope you have a good rest of your day.